A radioactive material of thermal conductivity K is cast as a solid sphere of radius R0 and placed in a liquid bath for which the temperature T infinity and convection coefficient H are known. Heat is uniformly generated within the solid at a volumetric rate of Q dot. Obtain the steady state radial temperature distribution in the solid, expressing your results in terms of R0, the radius of the sphere, Q dot, the volumetric generation, K, the conductivity of the material, H, the convective coefficient, and T infinity, the temperature of the surrounding. Knowing that the general equation in spherical coordinates is given by the following form. So as usual, first we start from the general form and we simplify it. So here, if we do a small scheme, we are in the case of a spherical geometry. That's why we need to use the equation for spherical coordinates, and it's given for us. So, and let us see, each sentence here will be used to do some simplifications. So first, they said that we have a steady state case. Whenever we have a steady state case, then this term will cancel out. So because of steady state. They also told us that we have only variation with the radius. And it's a 1D case, okay? Because of symmetry, no variation with angle. So temperature is varying only in R direction. So we can consider that del T by del phi and del T by del theta are equal to 0. And we just have variation with radial direction. So this is the term showing variation of temperature with R. Of course, this energy equation is for a solid. Okay, you remember in class, we have seen the general equation that can include, in case you have a fluid, you have the convective term also. But here, since it's a solid, so you only have conduction. Okay, then and also they told us that we have a uniform generation within the solid with a volumetric flow rate Q dot. So this term will remain in the equation. So after considering the given, we can say that our equation will reduce to 1 over R square del by del R of KR square del T by del R. And because T is only varying with R, you can replace del by D because you have only one variable, it's one dimensional. Okay, so plus Q dot equal to 0. And now all you have to do to solve for the temperature distribution, you need to integrate this equation twice, okay? And the constants can be calculated from the boundary conditions. Can you tell me, according to the given here, what will be the boundary conditions in this problem? I have a sphere and I have uniform generation Q dot within the sphere. And I know that the external conditions, we have convection with the external environment with a coefficient H and a temperature T infinity. Since this is a second order differential equation, I need two boundary conditions. Can you tell me what will be the two boundary conditions in this problem? First, how can you use the convective condition here? At steady state, okay, we have steady state conditions. And plus, we have that at the interface, okay? So if we consider just the external layer, the surface layer, okay? If I take a control volume over the surface layer, a very thin control volume, I can say that heat will enter this control volume by conduction process. and we'll leave it by convection. So the first condition, boundary conditions that I can write is Q conduction at R equal to the outer radius, R0, is equal to Q convection. And we know that the expression of Q conduction is minus K times the area. And here's the area. I will take the lateral area of the sphere at the radius R0. So this is the radius R0. We know that the exchange will take place through the whole lateral area of the sphere. So it's minus KR times del T by del R. This is the conduction rate equals to the convection rate, which is H times the same area, because convection also is taking place through the lateral area of the sphere. So it's A at R0 here, and this is del T by del R at R0, equal to H times area at R0 times delta T, which is T at R0 minus T infinity. Minus T infinity. So this is my first boundary condition that I can write. Okay. Now AR will simplify. So I need first to be able to replace in this equation, I need to get what is del T by del R. This is why I need to perform the first integration. Okay. And the second condition here is the symmetry, because here you have a symmetrical case. Since you have a symmetrical case, so heat will propagate from the center towards the outer radius in all directions. Because of this symmetrical effect, the maximum temperature will take place at the center of the sphere, okay? Because you are evacuating from the center towards the outer environment. So the second condition is maximum temperature at R equal to 0. And we can write the condition as del T or dt by dr here. As we said, del can be replaced by d because we have only variation with R. So dt by dr at R equal to 0 is 0, since we have, by symmetrical effect, maximum temperature at the center. So these are the two boundary conditions that will help us to solve for our constant C1 and C2. Let us do this together. So let us start first. As we said, the first step will be to find the expression of our differential equation. So as we said, after simplifying, we end up with the following relation. Okay. Now we need to integrate it twice. So we take a Q dot first to the other side. And then once we take it to the other side, we multiply it by R square. And since K is constant, we can take it outside of the derivative. So we end up with a derivative with respect to R of R squared dt by dr equals to minus Q dot R square over K. Now we are ready to perform the first integration. So if we integrate first this term, we get R squared dt by dr equals to, when we integrate this term, we have minus Q dot R cube over 3K plus constant 1. So this is the result after the first integration. Now, before performing the second integration, we divide all terms by R square to get dt by dr equals to minus Q dot R over 3K plus C1 over R square. So this is now our, after our first integration, we get this relation. And this relation should be integrated again to get T function of R. So now I'm ready to integrate again. We have integral of dt with respect to R is temperature with R equals to minus Q dot R square over 6K. And we know that when we integrate this term, the integral of 1 over R square is minus 1 over R. So minus C1 over R plus constant C2. So this is the form of our equation. It's a second degree equation. And we need to solve for the values of C1 and C2. So to start with, as we said, the first boundary condition is because of symmetry. The derivative of temperature with respect to position at R equals 0 is equal to 0. So because of this, if we go back to this relation and we replace R by 0, for R equals 0, dt by dr is equal to 0. From here, we deduce from this first condition, we deduce that C1 is equal to 0. We still have to solve for C2. To solve for C2, we'll use our second boundary condition. Okay, as we said, what is the second boundary condition? Is the application of energy balance at the surface of our sphere. Okay, we have minus K dt by dr at R0 equals to the convective coefficient times TR0 minus T infinity. Let us replace, okay? So we said that if we go back to the expression of dt by dr, okay, we have that dt by dr is minus Q dot R over 3K because we said that C1 is 0. So this term will cancel out, okay? And now if we replace at R0, we get that this is equal to minus K times minus Q dot R0 over 3K. So as you can see, K will cancel out. And minus minus will give us plus. So plus Q dot R0 over 3 is equal to H times. Now we have to replace TR0 by its expression, okay? So we go to this equation and we replace. So we have H times minus Q dot R0 square over 6K C1 is 0, so this term will cancel out, plus C2. And as you can see, this condition will give us the value of C2, okay? Because we can deduce from here that C2 is equal
في بلس تي انفينيتي مش هيك دكتور؟
minus T infinity أكيد minus T infinity. Okay. So C2 is equal to Q dot times R0 over 3H plus Q dot R0 square over 6K plus T infinity, okay? So in this way, we have calculated the value of C2, okay? And now we can replace C2 by its expression in the temperature profile. This will give us T as a function of R. So this is the general expression of T as a function of R, okay? Any question on this? Okay, let us do another problem. A plane wall is a composite of two materials, A and B. The wall of material A has uniform heat generation, Q dot, in watt per meter cube, equal to 1.5 times 10 to the power 6. we have that Ka is 75 watt per meter Kelvin, and the thickness La is 50 millimeter. The wall material B has no generation, with Kb equal to 150 watt per meter Kelvin, and thickness Lb equals to 20 millimeter. The inner surface of material A is well insulated, while the outer surface of material B is cooled by a water stream with T infinity equals to 30 degrees and H equals to 1000 watt per meter square Kelvin. We want to sketch the temperature distribution in the composite under steady state conditions, and we want to determine the temperature T0 of the insulated surface and the temperature T2 of the cooled surface. Okay, so please keep in mind to differentiate between whenever you have several layers, you need to solve for the equation in each layer separately. Okay, and here you have not only different conductivity, but also different condition. You have in material A, you have generation of heat, while in material B, you have pure conduction. Okay, and you want to solve for your temperatures, your extreme temperatures, T0 and T2. How can we think in such problem? First, we need to divide the analysis. We say we have two materials. We can say this is material A, okay? For material A, we have generation. So the conduction rate is not constant in the material, okay? And the temperature profile is not linear here. So since they asked us to sketch the distribution, we need to have the equation of variation in order to determine if it's linear, if it's second degree, third degree, etc. So we go back to our differential equation, okay? We know that in case of conduction in a solid with generation, after simplifying the equation in Cartesian coordinates, what do we get? We get the second derivative of temperature with respect to x plus Q dot, the volumetric generation, over the conductivity, okay, equal to 0. So I give you the general equation, and you do simplification exactly as we did in the previous problem. So you get the general form for steady state conduction with heat generation. So this is for material, this is the differential equation for material A. For material B, the difference is that we don't have generation. So for material B, we just have second derivative of T with respect to x equal to 0. And you can say that the derivative of T with respect to x is constant. Because the derivative of T with respect to x is constant in material B, then we can say that variation of temperature in B is linear. Okay? Because in material B, derivative of temperature with respect to time, with respect to x, sorry, in B, so dTB by dx is constant. And we can call this constant C1. Okay? Now, how to determine C1? To determine C1, we need to find the conduction flux through material B. And we can say, we know by definition that Q conduction in material B is equal to minus K times dTB by dx. And since dTB by dx is constant, equal to C1, so the conduction rate in material B is constant. Okay, of course, here this is the conduction flux, Q second. If you want the conduction rate, you just multiply by the area. But since here we don't have any information about the area, then we can work with the conduction flux. So the conduction flux is constant, equal to minus K times C1. Okay, now, how to get this conduction flux? What do we know in this problem? In this problem, we know that we have from the external side free convection. Okay, so first, if we take this interface at this level, we can say that Q second conduction exiting material B will exit to the outer environment by convection. Okay, so Q second conduction, which is constant, is equal to Q second convection. So this is equal so if you want minus K, okay? Now, if we want to replace dt by dx, we can replace it by T2 minus T1 over LB. So T2, because it's constant, so we just take the slope. dt by dx is constant. We take the slope of the straight line, which is T2 minus T1 over LB. Is equal to the convective coefficient H times T at the surface, which is T2, minus the ambient temperature, T infinity. Okay, so as you can see here, in this equation, we have two unknowns. We don't know T2 and we don't know T1. So we need to get an additional information that will allow us to solve for our temperatures. Let us think together. This conduction flux is coming from material A. Okay, so the source of this conduction flux is coming from material A. In order to calculate the conduction flux exiting material A at this level, what can we do? We know that Q second is not constant in material A. That's why here the best approach is to consider the macro scale approach. What do I mean by macro scale? I consider the whole material A, okay? And I do an energy balance for this material. At this level, it's insulated. So you have insulation, no heat rate. Within the material, you have generation, okay? So what can be your equation? You can say that, you know, the general equation in steady state, okay? In steady state condition for a certain control volume, we can say that E dot generated plus E dot N minus E dot out equals to 0, okay? In general case, it's equal to a derivative to the storage term. It's equal to derivative of energy stored with respect to time. But here it's a steady state application, okay? There is no energy storage in this case. That's why, because of steady state, these terms cancel out, equal to 0. For this control volume, we don't have an inlet because here it's insulated. So E dot N is 0. We just have an outlet. And the outlet, at the outlet, what do we have? We have conduction from material A towards material B, okay? So we can say now that this E dot generation is equal to the rate of conduction, Q conduction, at which location? At X equal LA, okay? Because conduction is varying. If you take an interface here, the conduction here will just be equal to the generation in this small part. And if you do energy balance to this small part, Q conduction at this level equal to generation in this volume. And as you go away from the insulated surface, Q conduction will increase. Why? because the volume of generation will increase. And the maximum volume is here at the interface between A and B. So at the interface between A and B, you'll have the maximum conduction in material A. And how to calculate Q conduction at LA? You just have to say it's equal to E dot generation. How to calculate E dot generation? It's Q dot, which is volumetric uniform generation, times the volume of material A. Okay, and the volume of material A is just the area times the length. So it's Q dot times area times length, LA. Okay, now this is equal to what? To the conduction rate. How we write the conduction rate? It's the conduction flux times the area. So it's equal to Q second conduction times area. The area now will cancel out. So you will be able to calculate what is the rate of conduction leaving material A. The rate of the flux of conduction leaving material A is Q dot times LA. Okay, so now you can say that this is equal to Q dot times the length of material A. You have Q dot, you have LA, you have T infinity and H. You start by using this equation to get T2. Once you get T2, you replace T2 in this equation, you get T1. So this is how you can solve for temperatures T1 and T2. Any question on this? Last step, we still need to solve for T0, okay? To solve for T0, we need to go back to our differential equation because we need T as a function of X. And then we say that T0 corresponds to X equal to 0. So if I integrate this equation 2 times, I get T of X. And then I say T0 corresponds to X equal to 0. Let us do this together again. So let us remember the steps again. So first, we can start by doing a sketch. As we said, to sketch the temperature variation, we know that in B it's linear, and material A it's second degree. It's second degree because the second derivative is constant. As we have seen here together, the second derivative is minus Q dot over K. So if you integrate 2 times this equation, you will get a second order equation. T is function of X squared. And of course, because you have insulation here, due to insulation, the maximum temperature will take place at X equals 0. Okay, so if we want to draw the profile of temperature, we can draw a second degree parabola having a maximum at X equals 0. So here we have a maximum. And then you have a decrease of temperature, okay? And at this point, if you want, the slope will be the highest. dt by dx is the highest at the interface between A and B, because as we mentioned, Q conduction will be maximum at this level. Happen in material B. In material B, we said to be able to know if the slope is smaller or larger than this slope here, we need to write the continuity equation, the continuity of heat at the interface. What do we mean by this? At the interface, we have Q second, which is the conduction flux in material A, is equal to Q second in material B. And we know what is the expression of Q conduction. So you have minus K. Actually, what is the same as the rate, okay? But because the area is the same, and here you have A, and here you have A, the rate of conduction is the same. And since the area is the same for both walls, the area will cancel out. and the flux of conduction at interface between A and B is the same. Okay, so conduction leaving A, flux of conduction leaving A is equal to the flux of conduction entering B. And we can write that minus Ka dt by dx in material A is equal to minus Kb times dt by dx in material B. Okay, so you can say now, I can deduce the relation between slopes. So we can say that dt by dx in material B is equal to Ka over Kb of dt by dx in material A. And you have the values for Ka and Kb. Ka is 75, Kb is 150, so this is 0.5. This means that the slope in material B is smaller than the slope in material A. So here suddenly the slope will vary, okay? It will be divided by 2 and then it will continue in a linear way. So this is how you can draw the profile of variation of temperature in your walls, okay? So as you can see here, maximum temperature at x equals 0. Then here suddenly the slope will be reduced by 2 because of different conductivities of materials, okay? And here finally you have the convective coefficient. Because of convective condition, you have sudden drop in temperature from T2 to T infinity. Okay, and now as we said, to solve, we first we do energy balance here first, okay? And we say that you can do the energy balance if you want from the beginning for the two walls. And if you take the whole system, okay? You can also say that generation in this material, which is just restricted to material A, is equal to the convection flux. So you can start by putting this condition in order to get the value of T2, okay? So you have generation equal to E out. So Q times ALA equal to AQ second. Then you can solve for T2. And once you solve for T2, you can go back to the condition in material B. You say that this flux is equal to Q conduction in material B. And then you can solve for T1, okay? Finally, to solve for T0, you need to consider